that we've been able to resolve now. So for those of you who have sent message to me in the past, I think I'll be able to reply to them because I noticed some of them came into my spam box. So for everything now rectify. So in case you send me a message and you haven't gotten the reply, make sure you reach out again, okay? Okay, so we want to go into days. 1 second, I think I corrected that date. Let me see. Yep. Earlier in the week, we started deriving the moment generating functions of some selected discrete probability distribution. I've been able to derive the moment generating function for binomial, for geometric and negative binomial distributions. The focus today, we're going to focus on two other discrete probability distributions that we'll call the Poisson and the discrete uniform. Of course, in tomorrow's lab, my TA is going to walk you through all the examples on this on the materials for the week. So, what we actually want to show, I'm quickly going to go into the summary table of what we actually want to show today, and I need you to pay attention why this is going on. Now, take a look at this. This is going to be in focus. Okay, so we want to derive these two. Okay, we want to derive the moment generating function of Poisson distribution of discrete uniform. I wanted to start with Poisson distribution. Okay, I wanted to start with Poisson distribution. Please make sure you focus. For Poisson distribution, okay, if I have a random variable s, follow poi with parameter lambda, the probability of s equal to s is exponential raised to power this, lambda raised to power s over x factorial, and then start for 1, 0, 2, until it continues to go to infinity. This is a distribution that we use to model the occurrence of events in an interval. And of course, we've derived the mean and variance of this distribution initially. Or expected value of that is that, and the variance of that is that. But what we want to derive today is the moment generating function of a Poisson distribution. The moment generating function is defined as this, expected value of e raised to power ts. For discrete random variable, it's actually this. Okay, for all discrete random variable, it's actually that. Okay, now the ms of t, because the state space or the support for the Poisson is from start from 0 to infinity, e raised to power that, and that guy is actually going to be this lambda raised to power s over s factorial. Please, I need you to pay attention to what I'm going to be doing right now. So right now, okay, this is independent of x. If I actually bring it out, if I bring this guy out, I'm actually going to have s start from 0 to infinity if I combine this and that. So I'm going to have e raised to power t, lambda, everything raised to power x, divided by x factorial. Now, who doesn't know how I combine this and this? because this is raised to power s, and e raised to power t also have an s, so I can actually bring them together. If you take a look at what I have here, whenever we have a sum to infinity, we have something carrying s, and we also have s factorial. Okay, so this, okay, so if you recall that summation s start from 0 to infinity, okay, maybe m raised to power x over x factorial is e raised to power m. Okay, from maths, if you recall that. So here, you're actually going to see that your m is this guy. So, which imply m is this guy. So, if m is that guy, then it means I can rewrite this summation s start from 0 to that e raised to power this divided by x factorial. So this is going to be the same thing as this. Okay, so using this. So if I want to rewrite the moment generating function now, okay, I'm actually going to have this one, then I'm going to have this guy. Now, if you combine these two, okay, so we're going to have this guy minus that. So when you factorize that, where lambda is common, you're actually going to have this. So this is the moment generating function of a Poisson distribution. So what you're seeing here. So that is what we just derived. Is there any question, whether in person or online, on this? Is there any question on how we derive the moment generating function of a Poisson distribution? Is there any question? If you want to investigate the validity of this, of moment generating function, all what you need to do is to plug in 0 for t. When you plug in 0 here, there's going to be 1 minus 1, which is going to be 0. 0 times that, and it's raised to power 0 is going to be 1. So whatever distribution you're giving, of course, you actually, going to use that. Now, let's say you want to derive, let's say from this moment generating function now, okay, they want you to derive, okay, e of s squared, okay, e of x3, and so on. Maybe even the variance of s, from the given, from that moment generating function. Okay, I need you to pay attention. Okay, if I want to get this, I will need to first differentiate the moment generating function. I want to differentiate this guy. The moment generating function, okay, the moment generating function. Can you hear me, right? Okay, the moment generating function of the Poisson, we have it as, e raised to power lambda, e raised to power t minus 1, that we can also rewrite as this. Okay, that we can also rewrite as that. Okay, now if I differentiate this guy now, differentiating that means I want to differentiate with respect to t. Okay, now I needed to pay attention to how I was going to differentiate this guy. If you block this, you differentiate with respect to t. This is going to be 0. I'm only going to have that. I'm going to have lambda that, then all of that. Look at that. I've differentiated this. How? You block this guy, differentiate what you have at the top with respect to t. It's just going to give you this. Then you rewrite the exponential, because that's the way we differentiate exponential function. So right now, my expected value of s is when I now plug in 0 after 0 for t, after the first derivative, so which is the ms of t or dt when t equal to 0. So I'm actually going to introduce that. I'm introducing that now. So right now, so lambda, this is going to be 1. Then I'm going to have lambda minus lambda. So this is going to be lambda e raised to the power 0. And what do you have? So which means the expected value of s, which is m prime x of 0 equal to lambda. Okay, this is how we can derive the mean, or, using the moment generating function, okay, for Poisson distribution. If we want to obtain the expected value of s squared, okay, if we want to obtain the expected value of s squared, as for the expected value of s squared, I need to differentiate again m prime x of t. So which is, I'm actually want to do the squared ms of t, or, the t squared. Okay, so which means I'm actually going to, please pay attention. I'm actually going to come here to what I've differentiated before. Okay, there's a function, I can split this guy into 2. There's a function of t. This is another function of t, right? Then I'm going to use a product rule. In a product rule, I'm actually going to write one, differentiate the other, plus write the other one, differentiate the other one. So right now, if I write this guy, okay, writing this guy, now differentiating this, don't forget differentiating this give us all of that. Now I'm now going to write all of that. Can you see that? Which means I wrote this, I differentiate this, then plus, I'm going to write this guy now. I'm going to write that guy now. Okay, I've written this guy, then I'm going to differentiate this guy. So differentiate this guy, I'm still going to have this guy. So this now become expected value of s squared when I'm actually plugging 0. When I plug in 0, okay, when I plug in 0 now, I'm going to plug in 0 to wherever I see t. So lambda is 0. Lambda is 0, then plus is 0, lambda is 0. So right now, there's going to be lambda squared, because 1, 1, 1, that's also going to be 1 plus, so this is going to be lambda. So expectation of s squared now is actually this. Or automatically, I can figure out what the variance is actually going to be. Don't forget, this is the same thing as m prime x of 0 minus m prime s of 0 all squared. Okay, so right now, this guy, lambda squared plus lambda minus the square of what we got before. So what happened? That gave me lambda. So which means the variance of s is also lambda. Now, what have we done? We have, using the moment generating function, we derive the mean and the variance, of a Poisson distribution after deriving the moment generating function. Is there any question on this? Okay, you can see my writing clearly, right? Okay. If you don't understand, if you get stuck, whether you are streaming online or you are in person, please ask question. So now, another thing that I want to talk about, if I have to, how do we, if x follow Poisson distribution with a certain parameter, and y follow Poisson distribution with another parameter, now how do we figure out the moment generating function of the sum of the two Poisson random variables? That's what I want to talk about now. Okay? That's what I want to talk about now. Please, I need you to pay attention. I need you to pay attention. Okay? Now, I want to talk about the sum, I want to talk about deriving MGF of the sum of the sum of two Poisson random variables. Okay. Now what happens is this. If X follow Poi with parameter lambda 1, okay, and Y also follow Poisson with parameter lambda 2, okay, we have two different variables follow Poisson distribution. Now, and the question I'll say, find the moment generating function, okay, of the total. Okay. Now, we want to find the moment generating function of the total means I want to find the moment generating function of S plus Y, of S and Y. So now this is what you're going to do. I need you to pay attention. If X is a random variable, Y is a random variable, S follow Poisson, Y follow Poisson, and they are independent, then we can make use of this. The moment generating function of the sum of random variable equal the product of the respective moment generating function. Okay, this is the rule. Okay, so right now, if X follow Poisson, okay, what is a moment generating function? You know, if S follow Poisson, of course, the moment generating function is what we derived the other time. So it's actually going to be e raised to power, then I'm going to say lambda 1 et minus 1 for X. This is for X. For Y, okay, for Y, I'm going to write the same, except that I'm going to put lambda 2 et minus 1. Look at that. Because this has lambda 2, that has lambda 1. So right now, if I now want to figure how the moment generating function, okay, of the sum, okay, using this multiplied by that, it's going to be this multiplied by that. So it's going to be that 1, et minus 1, et minus 1. So by the time you multiply that, you write just one exponential, then you're going to add what you have at the top, right? You're going to add this guy. So when you simplify that now, you know, this guy is common, right? So if you bring that guy out, then you're going to have lambda 1 plus lambda 2. Now, right now, this is the moment generating function of the sum. Okay, if this is the moment generating function of a random variable S that follow Poisson with parameter lambda 1, and this is a moment generating function of a random variable Y that follow Poisson with parameter lambda 2, then this is how to get the sum or the moment generating function of the sum of these two independent random variables. We're going to multiply that, and at the end of the day, we have this. But let me tell you this. If I ask you about the distribution, what can you conclude about the distribution of that guy now? Okay, if I ask you, well, what are you going to conclude about the distribution now? I need you to pay attention. Okay, so what are you going to conclude about the distribution now? You know, if X follow Poi with parameter lambda 1, please pay attention. With parameter lambda 1, the probability mass function for that is this lambda 1 raised to power X over X factorial. Now, if Y follow Poi with parameter lambda 2, the probability of Y equal to that exponential raised to power lambda 2 raised to power Y over Y factorial. Now, X plus Y, please pay attention. X plus Y will now follow. X plus Y will follow Poisson distribution now. So what do you think what is the difference? Take a look at this. If this is a moment generating function for X, and this is the moment generating function for S plus Y, then it means we're just adding the two parameters. So, which means I'm actually going to have that. So if I want to write the distribution for this, now I'm now going to say the distribution of x plus y, okay, is now going to be exponential raised to power lambda 1 plus lambda 2, okay, lambda 1 plus lambda 2, okay, raised to power, okay, x plus y divided by x plus y factorial. Look at that. This is the moment there is a function, sorry, this is the probability mass function of the sum. So if you let the sum, let's say we say z is x plus y. If z is x plus y, if I'm going to rewrite this, I'm just going to write the probability of z equal to small z equal this into lambda 1 plus lambda 2. Okay, so lambda 1 plus lambda 2 raised to power z over z factorial. Then I can now say where z start from 0, 1, 2, and go on like that. So what am I trying to say? This is the probability distribution for the sum of two random variables that follow Poisson distribution. Okay, you can see or what I've done. You know, as a very quick example, I know my TA is still gonna. My TA. Can I say this? Please pay attention. Okay. If I have a distribution like this, can somebody tell me, without doing anything, what would be the expected value of z? What would be the mean of z in this? Can somebody tell me? You know the mean of x to be lambda 1. You know the mean, because look at that. Lambda 1 is a parameter here. Expected value of x for Poisson will be lambda 1. Here, expected value of y will be lambda 2. Can somebody tell me what will be the expected value of z? And don't forget, z is x plus y. Z, you want to find the expected value of the sum of the random variable. But you know the individual mean, you know the mean for each individual. Can somebody tell me? Well, the question I'm asking is this. Somebody asks you, what is the expectation of z? Or what is the expectation of x plus y in this situation? Can somebody tell me? What does it mean? What is the expectation of x plus y? When you go ahead. Exactly. It's going to be lambda 1 plus lambda 2. Send me a message for extra credit. Because here, this is the same thing as e of x plus e of y. And you know what? The e of x is lambda 1. The e of y is lambda 2. All what you just need to do is lambda 1 plus lambda 2. This is the expectation of z. Can you see that? You know, if I really want to know if I have this as a mass function for Poisson, the mean is lambda 1 here. For this one, the mean is lambda 2. Okay? If I'm adding them up, then the mean will be lambda 1 plus lambda 2. Okay? Okay, so let me quickly chip in one example before I go to discrete uniform. For this, I'm going to chip one example now. Please pay attention. I'm going to chip in one example before I go into discrete uniform. Okay. Now, a hospital receives an average of 4 emergency calls per hour from ambulance in unit A. Okay. So, example. Okay, a hospital receives an average of 4 emergency calls per hour from ambulance for ambulance unit A, and 3 emergency calls per hour from ambulance unit B. Okay. Now, the question is, what is the total, what is the total average? What is the total average number of emergency, average number of emergency calls per hour? Please pay attention. Okay, there are two ambulance units in a particular clinic. You know, whenever you talk about receiving emergency call follow Poisson distribution, okay, now if you take a look at this, I want you to apply, okay, the sum of the random variable. If you want to answer this question, please pay attention. Okay, if I let number of calls in unit A to be that, and that follow Poisson with what is the emergency call 4, okay, that lambda equal to 4 here. Then for the other unit, also follow Poisson, the emergency call is 3. Okay, I needed to pay attention. Emergency call is 3. Now, I need somebody to tell me what they wanted to figure out. Number one, what is the distribution? What would be the distribution? What am I going to write here? What would be the distribution of x plus y if you follow what I've done? Okay, can somebody tell me? What are you going to put here? Can somebody tell me? What would be the parameter for the sum of x plus y? If the lambda is 4 here, the lambda is 3 here. Can somebody tell me what am I going to put here? Eh? Good job. Send me a message for extra credit. Why 7? Because you are adding lambda 1 to lambda 2. So this is going to be 7. If this is 7 now, can somebody tell me the average? What would be the average? Huh? It's going to be 7. Who said that? Thank you. Send me a message for extra credit. The average is going to be 7. Done. So if I'm going to do moment generating function here, okay, all what I'm just going to do, what is the moment generating function for this one? Okay, the moment generating function for the first one, if you come here and only change lambda to 4, e to the 4 power, et minus 1. This is the moment generating function for the first one. For the second one, the moment generating function is going to be this. You just change the lambda equal into that. What is going to be the sum of the moment generating function now, or the moment generating function of the sum now, okay, is multiplying this by that. If you multiply this by that, you know what you're going to get? You're going to be adding that, right? Which is going to be 7 et minus 1. This is the moment generating function now for the total. Can you see that? Okay. I want to go to discrete uniform, which is going to be the last today. Okay, I want to welcome you to discrete uniform distribution. As for the discrete uniform distribution, of course, we apply discrete uniform distribution when you are selecting at random and you give an equal chance. You give an equal chance, to every element in the population you're choosing from. Now, let's go into want to derive this. For the discrete uniform, want to derive the moment generating function. Now, x, for discrete uniform, okay, x follow discrete uniform, okay. Now, the parameters, if I have that, I'm actually gonna say, the probability of x, that is 1 over n, and my state space 1, 2, 3, until I get to n. Okay, this is discrete uniform, very easy. You give an equal chance to. Now, if you take a look at what I have, I want to derive the moment generating function, of course, which is expected value of that. Okay, expected value of that. And for discrete random variable, so I'm actually having that, the probability of x equal to x. Okay, so right now, I'm actually going to have S star from 1. Okay, S star from 1 to n, e raised to power ts, then 1 over n. Okay, so 1 over n is constant, right? I bring it out. Okay, so 1 over n, then I'm having S star from 1 to n, e raised to power ts. Okay, so right now, 1 over n, so plug in 1, this is e raised to power t, plus when you plug in 2, that would be 2t. When you plug in that, so you're going to continue to go until you get to when you plug in that. Do you see that? Now, what kind of series is that? That is geometric series. How do I know it's geometric series? Because it has a common ratio. So this divided by this is going to give you this divided by that. Okay, then you have to remember what is the formula for finding the sum to n tan in a geometric series. You did this in high school. You're going to see something like this. Has anybody seen something like this before? This is what you did in high school, sum. So here, your A here is e raised to power t, and your R is also e to the a raised to power of t. This is the first time, and the common ratio is that. So if I'm going to rewrite that, I'm actually going to have ms of t equal 1 over n. So I'm actually going to have e raised to power t, into e raised to power t into 1 minus e to the t n, because that divided by 1 minus e to the t. I just wanted to look at that. Look at what I got. Now, look at this guy now. Okay, this is a moment generation function of a discrete uniform, which is what you have here. Can you see that? That's beautiful. You're just making use of your knowledge in high school. That's why the knowledge in high school is very relevant to whatever you're going to be doing here. Okay, relevant to that. Okay, but let me tell you this. How do we check for this? If we normally plug in 0, right? I need every one of you now. Plug in 0, tell me what you get. Plug in 0 for t and tell me what you get. There's going to be issue. Try that. Let's see. Plug in 0. What do you get? Plug in 0. What do you get? Are you doing that? Plug in 0 wherever you see t. Because while we plug in 0 for t, that's the way to check the validity of the moment generating function you derive. What do you get when you plug in 0? When you plug in 0 for t, what do you get? Huh? You're going to get is 0 divided by 0. Whenever you have the 0 divided by 0, has anybody heard about L'Hopital's rule? Okay? L'Hopital's rule. Okay? Because I want to evaluate this. I want to set t to 0. When I set it to 0, okay, so, when t equal to 0, this is going to be 0 over 0. 0 over 0 is undefined. You know what you're going to do? Now, we want to apply L'Hopital's rule now, where we're going to, we want to find the limit as t tends to 0, okay, of 1 over n, e to the t into 1 minus this, divided by that. We want to evaluate this, using L'Hopital's rule. But if you, the very first thing we're going to do, I'm actually going to say t to the 0, 1 over n, multiplied by another limit, t tends to 0, e raised to power t, which is this guy. Then another one, limit, t tends to 0, 1 minus this, divided by this. Look at that. Look at the way I'm splitting that. Because the limit of a complicated function can be the product of the limit of several components in the system. So look at what I'm doing now. Please pay attention. Okay? Pay attention. For this one, this is a constant. The limit of a constant is going to be a constant, right? That's going to be 1 over n. Here, set it to 0. That's going to be 1, right? That's going to be 1. So I got 1. That's going to be 1. Now here, when I set t to 0, I'm actually going to have a 0 over 0, right? I'm going to use L'Hopital's rule. Okay, so here to use L'Hopital's rule, now you are not going to use a quotient rule to differentiate. Now, this is what L'Hopital's rule is talking about. Are you ready? Are you looking at the board? The L'Hopital's rule is going to say, differentiate the top one, also differentiate the bottom one. So I want to differentiate. So right now, you're going to differentiate this guy. Please pay attention. Okay, you know what we here, this already give us 1 over n. We don't have issue with this one. So here, because the L'Hopital said if I have a limit of f of s divided by limit of g of s, and you know, when I set, when s tend to whatever, and s tend to whatever, if I have 0 over 0, L'Hopital said differentiate this, differentiate that, then set the limit again. Okay, set the limit again. So what I'm going to do, I will differentiate this one with respect to t. Please pay attention. When I differentiate this guy, this is 0. Okay, with respect to t, so I'm actually going to have negative n e to the tn. That is how to differentiate this. Divided by differentiating this one is going to be negative e to the t power. Okay, then what I'm going to do now, I'm now going to set it to 0 again. Okay, when I set it to 0 here, 1 second. Where are you? Okay, when I set it to 0 here, okay, I'm actually going to have negative n because it's going to be 1, and this is going to be negative 1. So what do I have here? N. Now, that very n, then I'm going to write it here to multiply that. What happened now? N cancel n. What do I have? 1. That is how to investigate the validity here. You know, we're investigating this. We're actually investigating that the moment generating function has to be equal to 1. So can you see that? So that's how we that's how we do that. Okay, so can we also have, I want to give you a real life example, you know, on this discrete uniform, you know, can we also talk about deriving the sum of random variable? Okay, I'm going to use an example that you're going to like. Maybe I should use example from from my quality control. Okay, now you have a quality control inspector. Okay, the quality control inspector selects one product from machine A randomly, and it selects another product from machine B randomly. Okay, so you have machine A. So I'm going to talk about example right now. So you have machine A, you have machine B. Okay, now it selects one product randomly, and inspector, the inspector that wants to make sure that what is produced from this machine conform to specified standard. So it selects one randomly from the product produced by machine A, and select another one from product produced by machine B. Now, when it selects this, it's actually going to assign quality score. Please pay attention. Quality score. Okay, for each product, the quality score ranges from 1 to 5. 5 is the best. 1 is poor quality. Does that make sense? So 1 to 5. Now, the question now has, assuming 2 inspectors are independent, assuming 2 inspections are independent, okay, assuming 2 inspections are independent, or let me just say 2 inspectors, okay, let's say this is what happened. We have two inspectors. One randomly select product from machine A. Another inspector select from machine B, but they are independent. And the quality score, each of them going to assign to the product is 1 to 5. Now the question now say, find the moment generating function of the total quality score. Find the MGF of the total quality score. Now, this is going to follow uniform, discrete uniform. Why? The quality score is 1, 2, 3, 4, 5, and the inspector choose products at random. Now, if I'm going to write the distribution, if I'm going to solve this problem now, please pay attention. Okay? If I'm going to solve this problem now, okay, I'm actually going to say S follow discrete uniform with 1, 2, 3, 4, 5. Okay? Now, which means here, the probability of assigning is 1 over n, because you can assign, depending on the nature of the product, you can assign any of this. This is equally. So this is going to be that here S is 1, 2, 3, 4, 5. Then the second product also follow discrete uniform. Okay, also follow discrete uniform. The probability of y equal to this is also 1 over n, and y is 1, 2, 3, 4, 5. Now the question now is find the moment generating function. Okay, but what is the moment generating function of the first one? What is the moment generating function? Okay, of the first one? You already know the moment. Please pay attention. Pay attention. You already know that this is the moment generating function, right? For the discrete. Now you're going to write ET 1 minus instead of n. Instead of n, you're going to write 5. Instead of n, you're going to write 5. Okay, so this is going to be 5t divided by 5, 1 minus, what do you think I'm plugging in for n? In a discrete, the last number, okay, the last number is actually what you're going to plug in. Now, for the y, it's still going to be the same. It's still going to be the same for the y. The only let's say for instance, if the space here is different from the state space here, then you don't expect them to have the same number. They're having 5 and 5 right now for n because the support is from 1 to 5. Can somebody tell me now? What am I going to do to get the moment generating function of, okay, what am I going to do? I want to get the moment generating function of the sum of x plus y. Somebody tell me, what am I going to do to get the moment? I know the moment generating function of each, but I want to get a moment generating function of the sum of x plus y. That was what it says. Look at that. Find the moment generating function of the total quality score. The total quality score is when you add x to y. Don't forget, this is a quality score here for that product. This is a quality score here. So what am I going to do? I will use the law that says we multiply the respective moment generating function. So which means I'm multiplying this by this. Which means since this and this are the same, I'm only going to just do ET 1 minus this divided 5 into 1 minus this. I'm just going to put squared. What if it is 3 products? X plus Y plus Z. This is going to be raised to power 3. Done. Okay? That is done. Okay? That is done. So, in general, okay, this is now represent the moment generating function of the sum of the random variable, x and y, where x followed discrete, y followed discrete. Okay, this is it. This is our what we're going to do. Okay, now let me tell you what we're going to do next week. There's a lot of calculus next week. I'm just preparing your mind, because we're no longer going to be talking about discrete. We're going to be talking about continuous, and we're going to be talking about something that has to do with integral. Does that make sense? Well, let me say this. When you get stuck, you can now visit my office hour. My office hour is on Zoom. Every Friday, the Zoom link is working perfectly now. We have a new Zoom link. Okay? My office hour is 12 to 2 on Friday. 12 to 2 on Friday. But if that office hour is conflicting with your arrangement, please reach out to me. And for those of you who have reached out before and you've not gotten response from me, so I seriously apologize for that. Initially there was a kind of, in fact, I saw some of, some items were deleted, by the IT.